All right, so to wrap up this section here, we're going to be taking a look at equivalence relations, some classes, and partitions, right? So when we define equality in a relation, right, what we are referring to if a relation is an equivalence relation, right, then it has the properties of being reflexive, symmetric, and transitive, right? So when we think of this idea of equality, right, what we want to think of, right, when we think of equality, we think of it having these same properties, right? It's reflexive, something is equal to itself, right? Symmetric, if A equals B, B is equal to A, right? And it's transitive, right? Again, right? Good analogy with like real numbers, right? Right? That sense of equality is if these three things can hold, right? So any relation with these three properties behaves like equality. It groups things that are the same in some sense. So this, if a relation has these three properties, we say it is an equivalence relation. Okay, so a relation that is reflective, symmetric, and transitive is an equivalent relation. All right, let's work through one of these examples in the book here. So the book says that way. So it wants us to prove that the relation so they use this notation, right, which holds two integers. Two integers, if two integers if their difference is even. So I want to prove that it is an equivalence relation. So A, B, if and only if B minus, B minus A is equal to 2K, where K is some integer. Okay. So again, we want to run through that. Is it reflexive? Right? Okay. So one. So here, let's say that A minus A, right, that's equal to 0, or you can think of it as 0 times 2 times 0. Right, 0 is an integer. Right, so in this case, K is 0. So it is reflexive. Right, so A, this is true. All right. Is it symmetric? Okay, so if it is symmetric, then here we have, so let's assume A minus B is 2K. Then B minus A would be equal to negative 2K, but I can just write that as 2 times negative K. Right, so now the difference of A minus B is even, but so is B minus A. Right, negative K also an integer. Okay, so here is the same. So it is it is symmetric. Now, is it transitive? Okay, so 3, if it's transitive, so let's assume that A minus B is 2k and B minus C is 2j. All right. So in other words, my assumptions are A to B, B, C. Now let's prove that A has the same relation to C. So what about A minus C? Well, I can treat A minus C as A minus B plus B minus C, or A minus B, factor out a negative, C minus B, right? And here A minus B we saw was 2k, and C minus B, all right. Okay, actually, could have just left it like that. B minus C. And done. Okay, so A minus B is equal to 2k, and here we have, okay, B minus C is equal to 2j. Okay, actually I didn't just work up here. Okay, so here we have, I need to factor out the negative. A minus B I define as 2k, and then B minus C as 2j. Could factor out the 2. And again, k plus j is just an even integer. All right, so now we have that A has the same relation to C, right? So transitive property checks out. So now we can conclude here that this relation is an equivalence relation. Okay, all right, now a couple of other things here is this idea of classes, right? So when we're talking about classes, right, what we are referring to is the relation class. So if we recall here, so classes, right, so we define the relation class as the relation class of A, right, is the set where B is some element of A, right, and AB is an element of the relation R. All right, so the class of A are all the elements in the ordered pair would be of B, right? So, for example, when we did the multiple of, right, we define our set A to be the numbers 1, 2, 3, 4, 5, and 6. Okay, now the class of 1 would be all the ordered pairs where the second number was 1. Well, in that case, that was only 1, right? The only multiple of 1 was 1. So 2 consisted of the only multiples of 2 were 1 and 2. All right, and then moving forward here, the relation class of 3 would be the set 1, 3. Relation class of 4, right? What are the multiples of 4? It was 1, 2, and 4. 5. The relation class there of 5 was 1 and 5, 1 in itself. And then lastly here, the relation class of 6 was 1, 2, 3, and 6. All right, now one thing to notice about these relation classes here is that while they do overlap, none of them are exactly the same, right? And that will always happen, right? They do partially overlap, but they won't always, none of them will be exactly the same here, right? So that is a relation class, right? The last thing here to wrap up this section is this idea of a partition, right? And a partition means, what this means is just given a set, right, we can partition it, cut it up however we like, right? A partition could be just another set where there will be subsets of our bigger set. In this case, I'll call it our set A, right? So I could say, all right, I could have this be 1, 2, and 3, 4, 5. Okay, now in this case, there will be no overlap between the subsets inside the partition, right? There will be completely disjoint, but the whole of it will make up all of our original set. And these partitions could be on either extreme, where you can make a partition where they're all of just one set, one element, I mean, and that covers all the elements in our original set. Or it could just be the partition is the whole set itself. So that would also be a proper part, or a partition, right? Okay, so that is how we a partition of a set.